Hey there, Earth Science fans. You ever make a fire sandcastle at the beach only to have the waves come in and destroy them later if the tide's coming in? I mean, what's with that? Kind of a bummer. Here's some example of tides. You got high tide on the left, low tide on the right, and then reversed over here. This is the Bay of Fundy, some of the largest tidal changes in the world. Some artists can even incorporate tides in their work. This is Sean Yoro, who creates giant murals that slowly get revealed as the tide lowers. And every day as the tide goes up, they get hidden again. And so he's working with tides to display his art. Andy Goldsworthy, one of my favorite artists of all time, sometimes creates sculptures that are actually meant to be destroyed by the tides. So as the tide comes in, they break apart his rock structures and carry them back out to sea. And I think it's a statement about how, art can be temporary and beautiful or momentary or something. I don't know. I just think it's a cool concept to use earth science in your artwork. All right, back to the basics just for a moment. What are tides? Well, this picture gives us a nice example with high tide on the left and low tide on the right. So tides are a change in the ocean level. Sometimes the ocean level is higher, and we call that high tide. And sometimes the ocean water level is lower, and that's called low tide. But what force could move that much water several times per day? All right, so this cartoon gives us a hint as to what causes tides. We have a cartoon moon on the left with a rope, little lasso, pulling on the earth, and that pulling is creating a little bulge here. So that's actually going to tell us a lot about how tides work. So what do you think this rope is representing here? Now you may know this already, but the moon pulls on the earth with its gravity, and actually the earth pulls on the moon a lot with its gravity as well. So there's this relationship between the moon and the earth where their gravitational attraction is affecting each other. Well, when the moon pulls on the earth with its gravity, it pulls on the water and creates this bulge here. And that's what high tide is. When the water gets pulled by the moon's gravity, it creates a higher tide because all that water rushes over to respond to the force of gravity. So we can look at it in a more scientific way as well. We talked already about the gravitational attraction, or this force of pulling between the moon and the earth. And on the side that faces the moon, because the moon's pulling on the earth with its gravity, the water rushes over, and we call it a tidal bulge, or the high tide. That's because the water rushes there, so there's more water over there than usual, and so that's what creates a high tide. And in my opinion, one of the great mysteries of earth science is that there's a tidal bulge on the far side too. So you have a high tide here facing the moon, and that's obvious because the moon's gravity pulls on the water there. But there's also a high tide here, and from my understanding, it's because the moon pulls on the earth a little bit too. So the earth goes this way, the water goes this way, and then some of the water over here, which is less affected by the gravity, remains there. So there's a high tide on the far side, a high tide on the near side to the moon, and then your low tides are going to be here and here. So it's not like the tides actually move. The tides don't come in and out. It's all about the rotation of the earth. So this idea of gravitational attraction between the moon and the earth and the rotation of the earth are the main drivers of tidal changes. Basically, let's say I'm at Rockaway Beach, and that's right here. If I'm in this point of Earth's rotation, because of the tidal bulge here and here, if Rockaway Beach is right here on the Earth, then I'm going to be in a low tide. And so the Earth is going to rotate around. Remember, the Earth rotates once every 24 hours. So about 6 hours later, I'll be a quarter of the way through my rotation. So 6 hours after this low tide, I'm going to have a high tide because the Earth's going to rotate into this far tidal bulge. 6 hours later, the Earth keeps rotating, and now I'm rotating back into a low tide. 6 hours later, now I'm rotating into this near tidal bulge or a high tide. So throughout a 24-hour rotation cycle, every location on Earth gets two tides. You have a low tide here and a low tide here, a high tide here, and a high tide here. So 4 tides total per 24-hour rotation. So definitely keep up with your thinking right questions. Remember, you're typing the answer right here below each question. And this time, we got a video of Sean Yorrell painting those tide murals that we talked about earlier in the lesson. There's also a cool time-lapse video of the Bay of Fundy tides, the largest tidal changes in the world. So definitely check those out and respond to the thinking right question. Okay, so we have our technical definition of tides here. The hourly change in water height caused by the moon's gravitational pull on Earth's large bodies of water. So oceans, large lakes, those kind of things are affected by tides. So we have the Earth's rotation and the moon's revolution being key for understanding tides. We talked about how as the Earth rotates around, you rotate into a high tide or a low tide. And the moon's revolution, because it also depends where the moon is on its orbit around the Earth, what types of tides and how extreme they're going to be on the Earth. So in general, like we talked about, if a side of Earth is facing the moon, that side will have a high tide because the moon's gravity will pull on the water. So if you're facing the moon, you're definitely going to have a high tide. There's 2 high tides and 2 low tides per day, which means there's a total of 4 tides. And because the Earth rotates every 24 hours, that means you're going to have a tidal change approximately every 6 hours, because 24 divided by 4 different tides means that each tide changes every 6 hours. And down here, a simple breakdown. So if my moon is here, then I'm going to have a high tide on the side facing the moon because the moon's gravity will pull on that high tide. And then that curious mystery about the high tide on the other side, which we talked about. So the high tides will always be in alignment with the side facing the moon and then the opposite side. So a line across between the Earth and the moon will show you where the high tides are. The low tides will also be lined up, but they will just be in the opposite positions from where the high tides are. And we have a graphic representation of tides as well. So over here we have on the x-axis, we have hours. This is a 24-hour cycle. On the y-axis, we have tidal height, or the height of the water. So if you start your cycle with a low tide, as in this example, about 6 hours later, you're going to have the next tide, which would be a high tide. If you started with a low tide, you'd go to the next one, which would be a high tide. And then 6 hours after that, you'd have your next low tide. 6 hours after that, you'd have your high tide. So in general, we have 2 high tides and 2 low tides per 24-hour cycle. You're going to start to cycle into your next tide. But remember that about every 6 hours, there's a new tide. So within 24 hours, there's about 4 full tide cycles within 24 hours. And lastly, I said that the moon's revolution was also important for understanding tides, and that's in these special types of tides. So these are special circumstances that only happen in certain parts of the month and certain parts of the moon's revolution around the Earth. And in this case, we're actually also going to bring the sun into it, because the sun exerts a strong gravitational pull on the Earth as well. So the moon and the sun both pull on the Earth with their respective gravities. So a spring tide is a stronger than usual tide, and it's when the Earth, moon, and sun are all lined up. So right here on the left side, we have a spring tide, and it's when they're all lined up, because the sun's gravity will pull over here, causing a really high tide, and the moon's gravity will pull over here, causing a really high tide. So when they're all lined up, the extra gravitational pull makes the high tides really extreme and the low tides extreme too, because all that water's getting pulled away. So a spring tide is a stronger than usual tide, and it could be lined up like this, or the sun, moon, and Earth could be lined up like this. Neap tides are weaker than usual tides, and it's when the sun, moon, and Earth are not lined up, so that they're not lined up, so they're pulling against each other. So in the spring tide they're all pulling together, which makes it stronger than usual. But when they're pulling in opposite directions or at like a 90-degree angle, the sun and the moon are not working together. So it's not going to be stronger than usual. It's actually going to be weaker than usual because, my high tide will always be on the side of the moon. So during high tide, if the sun is pulling this way and the moon is pulling this way, they're not working together. So it's going to create a larger than usual low tide and a lower than usual high tide. So that's why I say that the tides are weaker. The high tides are going to be a little lower. The low tides are going to be a little higher. It's not going to be as extreme as a spring tide. So the spring tide is strong and the neap tide is weak. Neap and weak kind of rhyme a little bit. I always remembered it like that. Neap is weak. All right, well, that's all for tides, and that's all for me today, and hope you guys are doing well, and I'll see you next time.